Hi, I'm DJ Ware. Today on the CyberGizmo, I'm going to be returning to a topic that I started when I first started this channel. A lot of people have been asking me to update that video because the audio was covered up pretty much by the background music. So I'm going to update it for today and also redo the topic of storage right after this. The reason I wanted to do a topic on storage to begin with was because the IT demand for storage is increasing at somewhere around 20 to 30% year over year. But it's more than just the amount of storage that is being demanded. I mean, the demand for storage last year was more than 42,000 exabytes. And that'd be about 42 zettabytes of data storage that the industry needed new. However, the supply for data storage only met about half that amount in last year, about 25,000 exabytes or 25 zettabytes. So there's a lot of reasons for that. Probably had more to do with budgetary constraints than it did actual, shortfalls in the ability to produce drives. I don't recall any shortages of disk drives last year, so it's probably more budgetary. But Forbes said that 79% of 112 respondents in 2017 indicated that their current storage architectures will just not be sufficient to handle their requirements over the next 5 years. So storage is a pretty important topic for the industry, but it's also a pretty important topic for the home as well. So I always like to start from the beginning because that's kind of where things kind of started. So the drive here that's on the left and the right is the very first hard drive. Before we had hard drives, the primary means of storing data was on punch card, paper tape, or magnetic tape. Those technologies have been around. The punch card has been around since the early 1900s. Paper tape has been around since at least the 1940s, probably a little bit before that as well. And mag tape, of course, has been around since the 30s. But so that was introduced in 1954 as the RAMAC 305. That cost about $3,200 a month in 1954 dollars. So today that'd be equivalent to around $29,000 a month in today's money. It only stored about 5 megabyte, and these were 6-bit words, not 8-bit. So IBM would tout this as holding about 62,000 punch cards, and those would be 80 columns. So you can figure out that's not a lot of storage. But the fastest form of secondary storage was the hard drive. I mean, we had RAM and then we had the disk, and that was much faster than any other medium. I mean, if you were to do a sort with, for example, punch cards, it took 2 passes to do an alphanumeric sort, 1 column at a time. So you ran through on column, let's say it was column 1 through 30. You would start with column 30, and then you would go to 29 and then 28, and you would sort on each one of those passes. But then you had to do the alpha part of the card as well. There was 2 pieces to make up an alphabetic character. If it was numbers, you could get by with a single pass, but if it was alphanumeric, you had to have 2. So yeah, it took quite a while to sort, and a tape sort wasn't any faster. So yeah, and paper tape you can't sort. Sorry about that. You'd have to sort it in memory and then write it back. You'd have to write out a new paper tape. Same thing with magnetic tape, by the way. You have to read it in and then write it back out. So usually it involved a 3rd drive somewhere. They took 3 tape drives to do a sort. It was pretty funny. But anyway, I digress. So, but these things required a lot of power, a lot of space. You can see it from the photo of the RAMAC. They even had to have a special plane in order to transport it. Each one of those weighed about a ton. And, well, here, the device, as can be seen here, there's actually 2 drives that were in the cabinet, plus the storage controller in the center. They were absolutely massive. The one in the middle here is I think that might be a Data General version of the drive, but that was manufactured by Control Data Corporation. They provided drives as an OEM to a number of computer vendors. We had one of these on a Honeywell system that was actually about 9 megabyte or so, not a tremendous amount of disk. And the SLED, or the single large expensive disk on the right, was the first actual enclosed hard drive or non-removable hard drive, which would be the Winchester Model 3030. And so that held about 30 megabytes is all. But as you can see, it's quite large as well. There's the one where the guy is rolling it around on a cart to, I guess, is in the manufacturing part of the business. But these things were expensive. Average price of the modern modern drives were anywhere from about $90,000 to $275,000. The last one was introduced in 1989 by IBM. It had 6 platters that you could purchase. The cost was about $50,000 to $100,000 depending upon how many platters you had. But it only stored about 22.7 gigabytes of data, had a transfer rate of about 4.2 megabytes per second. Yeah, megabytes per second. Fast by the day's standard, but not certainly fast by today's standard. I mean, you can go out and buy a 4 or 5 terabyte hard drive with 6 gigabit per second transfer rates now. Can you really achieve that? No, but, hey... That is what you could buy for probably less than to about $150 today. So, yeah, we've come a long way from that era. The reason for the change was the microcomputer directly attached storage. These were introduced in 1980 by Shugart, which is today called Seagate. The first drives were 5 meg. They were on a 5 megabyte, that's right. The same size as the RAMIC, except they used 8-bit words. They held they were 5 1/4. They were fairly big. But they were really meant to replace the floppy drives, and they did certainly do that. They weren't particularly fast because of the transfer rates of the internal connectors that were used in the machine were essentially a floppy controller. But they were faster than the floppy drive, and so they offered low power, low cooling requirements, and relatively, mediocre file transfer speeds. But those evolved from 5 megabyte. They shrunk down in size, went down to 3.5, and then finally 2.5 inch. And there was even some that were 1 inch, and some that were even fit on a SD card. But so today, as of this time, the largest drives that are available are 16 terabytes in the spinning Rust. And I would have to include, for direct attached storage, I would have to include SSDs and NVMEs because they are a form of directly attached. Doesn't matter what the interface is. It can be SATA, it can be SAS, it can be the PCI bus or the NVMe bus. So yeah, it doesn't really matter as long as they're still direct attached. And then this came. So this was the death knell for the DASD drives. In 1987, David Patterson, Garth Gibson, and Randy Katz wrote a paper that showed how you could take these inexpensive microcomputer attached storage devices, pair them together with a disk controller or a RAID controller, and you could do this either hardware or software, according to their paper, and they could be put together in such a way that these drives could not only exceed the storage capacity of the DASD drives, but they could also exceed the transfer rate of the DASD drives at a fraction of the cost. But, there's always, with good news, there's always a little bad news. And so anytime you add more hardware devices to a solution, you shorten the mean time to failure, meaning that the more drives you have, the less time passes between failures. So yeah, more devices increases the chance of a failure. But they had a number of in the paper, they had a number of descriptions for the way you could store the data in order to create these larger and larger drive arrays. The first was RAID 0. That's still around today. It's a striped disk. Single disk failure, total loss of data. So if you lose if you have a RAID 0 with a number of drives in it, any one of those drives fails, your entire storage system is gone. You have to recover from backup. RAID 1 is a mirrored, so this side mirrors that side. Or it can go that way as well, and this is the way the drawing is done. A1, and then there's another one. There's A to B1, C1, D1. So these drives mirror each other. So if you lose one of the drives in the mirror, then you can continue operating. If you lose more than that, then the mirror is dead, unless you're mirroring the drives all the way down. So if you have two A's, two B's, two C's, and two D's, then yeah, any single drive failure would cause a failure. But it has a high cost, in that half your storage is taken up by the mirror. There was also RAID 2, RAID 3, and RAID 4. I'm not aware of any of those being used today, but they were paid for by the military in order to come up with a way that we could continue operating the RAID even while we had a single disk failure. That was the goal. So the RAID 2 was basically a look at trying to use bit level striping with local parity. And then, since that wasn't really too good, RAID 3 was an improvement, and that was to use byte-level striping with local parity. RAID 4 was block-level striping with local parity, and it wasn't until we got to RAID 5, which is actually block-level with distributed parity, which is shown here, that we could actually achieve a single drive failure, and the RAID could continue to operate, although in a degraded mode. So yeah, but the downside of any of these, the RAID 5 and especially the RAID 6, they take quite a bit of time to restore in the event of a hard drive failure. And so what happened in the RAID 5 was, what they found is that if these drives are about the same age, and it's not a question of if a drive will fail, it's a question of when. So when a drive would fail, and you put in a new drive, it has to rebuild itself. And that rebuild process is very intensive. The drives are pretty busy until that member is included back in the RAID again and fully populated. Well, the strain on the other drives would be so high that another drive might fail at least the chances of another drive failing during the rebuild process were pretty good. And so RAID 6 was invented to try to circumvent that. And RAID 6 has, it's also block level striping, but it has double distributed parity, so you can lose up to 2 drives. And so that gave you a second chance if during the recovery you had a problem and needed to restore. But of course, RAID 6 takes a heck of a lot longer to restore than RAID 5 does. One of the drawbacks of RAID is that when it's rebuilding, it doesn't care if the block is empty or has data on it. It's still going to copy it. It doesn't know if there's data there or not, and so during the rebuild process, it just makes the assumption that there isn't, that there is data there, and goes ahead and copies it block by block. So yeah, it makes it pretty slow. I mean, if it's a large array, you're talking hours, days, maybe even a week or more to restore a large storage array. It has a number of hybrids. You can combine a lot of these together. You could combine these two, a RAID, a 0 striping RAID with a mirror, or you can combine a mirror with a RAID, or a striping with a RAID 5. You can do that. There's also one that's still included, which is called JBOD, which isn't really a RAID at all. It's just a bunch of disks. The other thing that kind of clobbered the DAS storage was the NAS, and the NAS actually was out before the RAID. So this was invented in 1980. It was originally called the Newcastle connection, and it was invented by Brian Randall, and he demonstrated that you could access a server remotely, access files on it, and he used Unix machines to do that. But that provides, directory and file sharing between multiple clients. So, and, they had NFS, and today we have Samba, and we also have iSCSI targets that can be accessed over a NAS. And usually the server takes and exposes either a directly attached storage device, in the case of a single drive, or it can expose a RAID. And it just looks like a file system to the client. It offers pretty good speed and convenience. I mean, it certainly paved the way to allow us to do file sharing, and a lot of the things that were made possible over the internet are because of the NAS. That protocol eventually led to the web server protocols and the way that they were kind of put together. It does require more network bandwidth than in one of Sun's ads back in the day. I think in the late 80s, early 90s was the network is the computer, and they were certainly right. Once a NAS is saturated, once you've saturated the machine itself, that is, I can't put any more clients on it, or I can't put any more DASD on it, or I've saturated the network, you've got to go out and get a new NAS and install it on the network. And then that means you have two endpoints for users to be able to attach to. Yeah, so that prompted the need for this, which was the storage area network, or the SAN. Brocade introduced that term in 1997 with the release of their fiber channel switches, which are shown here in the middle. So these were cross-connected and provided a redundant way of accessing the storage arrays from one or more servers. And the joke is that a lot of the companies that implemented solutions based on SAN were actually the members that had created the original mainframe DASD drives. And so we kind of felt like this was SLED's answer to NAS. That's what the SAN stood for, or simply it was just NAS spelled backwards. So that's how they came up with the name. But that was kind of the joke at the time. They're very expensive, and they're also very complicated, as you can see. But they do very well at providing the capabilities that they say they're going to. So they allow you to manage this large number of storage arrays as a single entity, or you can divide it up into multiple entities through the software, and then the access to it is controlled by the servers. You can have database servers, Linux servers, Windows servers, even VM machine servers that are accessing these pools, and then the clients themselves can access it over the internet using using exposed technologies, because these servers have to build and expose this as a file system, because the SAN itself doesn't create the file system, it's the servers that do. And so you can run NAS out here and then expose traditional NFS or CIFS or iSCSI targets, or even a database client can be accessed to. But the problem is that if these servers fail, that's a single point of failure, because those access points to the SAN are cut off. It is quite a bit more expensive than a NAS, obviously. And so, yeah, you only find these probably in server rooms. I don't mean to beat up on them too badly, because they do work, and they work very well, but they do come at a high cost. Generally speaking, this is a scale-up technology, meaning that I have to add drives to the servers. But once I've saturated the controller, or on the server here, or on the switch, I'm done. I basically have to come up with another way of managing a second SAN. And then that gets really complex in the storage fabric and also in the fiber fabric, in order to because now you have servers that are handling traffic from more than one SAN. So yeah, it gets very, very complicated and very costly. So what do we mean by scale up and scale out? So scale up is just adding additional drive arrays to the storage controller. And once the storage controller is maxed out, your scale up is done. Scale out is using kind of the same thing as scale up. I can add drives to each individual server. But then I can scale this out, because I can take those servers and I can add them together in a cluster, either via they communicate either over Ethernet. Some of them do fiber channel. There's not a lot of them that do that. and so it's either Ethernet or InfiniBand for the most part, and those form one or more storage pools. You'll typically find we have scale out right here behind me. But yeah, HPC environments were the first to utilize those because of the need for high performance storage. But there are a number of them that are cropping up in other locations as well. So yeah, I mean, Ceph is used today to manage VMs within a corporate infrastructure, and there are others that do that as well. So yeah, I mean, it's there, and we'll talk about some of those technologies as we get to them. So I generally consider RAID and SAN kind of things of the past, even though they're still supported today. And DASD is certainly around too. So I haven't really gotten away from any of the technology. It's just improved and gotten a lot faster. But one of the first big changes was designed by Sun Microsystems in the early 2000s, where they looked at the problems that RAID and SAN were causing, and they wanted to create a modern file system that didn't need all that hardware complexity. Wanted to push it back to making it more simple, creating a RAID that was more flexible and faster to recover. And they also wanted to include compression and encryption and copy on write, things that a modern file system would have. So it's basically divided up into a number of segments. You have a pool that you define at the top, which is comprised of one or more devices. Those devices can be mapped into a mirror or into a RAID. And there's various levels of RAID. I have videos on this, and so you can look at that. This one particularly is just a mirror where you have two mirrors making up a single pool, which is very possible in ZFS. It does offer some data integrity and data repair automatically. It does that as it's writing because there's a checksum that is maintained with each file. You can do snapshots, which is basically setting bars in time, where if you have some event that is unintentional, it changes the file system, you can roll back to a snapshot previous and restore the pool to its point in time. It also has deduplication, although it's recommended right now that we turn it off, but that allows ZFS to identify files that are the same, that are stored in different locations, and only keep one copy of it. The rebuild time on ZFS is much faster than a traditional RAID because it knows what it has written and it tracks it. And so when you go to rebuild a ZFS RAID, you're not down nearly as long as you would be with a traditional RAID because it only restores what is data, and it doesn't restore things that are blocks of data which are blank. But there is some problems. ZFS can use quite a bit of memory, particularly if deduplication is used. But like I said, right now it's recommended that we not use it. That will probably change soon. But the other thing is that the performance suffers when the storage pool begins to reach 70% saturation of the hard drive. So yeah, if you allow that to happen, its performance will begin to degrade very rapidly. However, the same can be said of most storage devices. When you get up above 70% on a hard drive and 90% on an SSD, SSDs not only slow down, but they wear out a lot faster because the Ware leveling algorithm within them can't find enough data space to move things around. And so, yeah, you end up wearing out an SSD much quicker. And as the size of a hard drive begins to fill, it gets harder and harder to store data and keep the directories to that data in a proper sequence to allow maximum performance. So, yeah, because you start writing to the centers of the disk, which don't hold as much, and the heads have to move more. Lustre was the first software scale-out platform, and it used a number of technologies in order to get that. It was developed by the Cluster File System Company, and it allowed me to create high-performance data pools that were shared with high-performance computers like Cray and some of those kinds of machines, but the superscalar machines. Sun, which acquired part of Cray, needed a file system that would be able to keep up with the Cray, because if you can't provide data fast enough, you starve the supercomputers from data. And so Sun acquired CFS, the company, in 2007. And of course, they in turn were acquired by Oracle in 2010. So I don't know what all transpired here, but I know that Oracle did not keep the Cray part of Sun, and they spun that off. And with it, since they did that, they didn't really have I believe that's the case. Correct me if I'm wrong, but I believe that was the case. They did not keep it. And since they didn't have the high-performance computing part, they didn't really have a need to keep Lustre either, and so they donated the source code for Lustre to the open source community in about the same year of 2010. Lustre provides a POSIX-compliant file system. It looks like a normal Linux file system to the Lustre client. It's made up of really 4 pieces. It has a metadata server right here, and then the metadata target, or the data that is about where to find the files within these different storage pools. The OSS is the object storage server, and this is the object storage target, and so you can have one or more of these. I don't know if Lustre can have more than one MDS. I haven't used it recently. In the times when I did, it did not. It only had one, but I think that it does now, but I'm not sure about that. And then, of course, it has to have its own client in order to make attachments. These can be the client machines that the users are running, or it can be servers that are exposing NAS again. Traditional NAS, to be able to share out files over the network. But it basically takes and creates a scale-out storage solution by providing a unified namespace to all of these files that are stored within the servers. The next one that came a couple years later was GlusterFS, and that was introduced in 2005. It's not related to Lustre in any way, and doesn't share any of the code as far as I know. Gluster provides a POSIX file system, and it's installed on top of a normal Linux file system. Usually it's XFS, because Silicon Graphics had built in the metadata support within the file system headers to permit it, because Silicon Graphics was a massive rendering platform that took files that were stored in a lot of different places within the network and then pulled them together to render out an animation and then push it back out. Now Silicon Graphics did a lot more than just that, but the reason for the XFS file system was to be able to keep information about the files, and Gluster uses that information in order to prevent it from needing a metadata server separately. Now, their thinking on this has been changed a bit in the past few years. They still do not need a metadata server, but I think their thinking is starting to track more to needing to create one. Because in order to find the metadata, they have to go to the bricks to get it. And that can be quite time-consuming to do, particularly if you have lots and lots of storage arrays. But it's designed for shared storage at scale, and Gluster is good at both object store, but not as good as Ceph. I mean, it's not because of the need to go out across the bricks. It's very good at file store, and it's very efficient, and it's very fast at doing it. It only needs 2 pieces. It needs a server and a client, and that's it. And the servers have the bricks attached directly to them. And those bricks can be ext4, they can be XFS, they can also be ZFS in order to do it. Now, ext4 is not as good as XFS or ZFS because they just simply do not have the constructs to store the metadata. But they recommend that this is installed in either a 10 gig Ethernet network or an InfiniBand, particularly for the network facing for the servers to use to communicate with themselves. And then you can use a 1 gig or a 10 gig Ethernet connection out to the clients. Depends upon how much data you have flowing between your servers and the clients. It is quite chatty, and I mean you can probably look back there and see that those things are moving around, even though they're not actively feeding up files right now. I have a couple of videos on Gluster, and GlusterFS was acquired by Red Hat in 2011. So it's part of the Red Hat family, and you can purchase support for it, but it is still available as a free and open source software platform. Runs on just about all of the platforms, including ARM, and the ARM is running back here on it. CEPH was introduced a couple of years later from Gluster. So every 2 years we seem to have something new coming up. So yeah, it was introduced in 2007. It's an object store, but it has other services that kind of provide block and traditional file system support. Rados provides the block storage capability within CEPH, and it's compliant with both S3 and OpenStack. So CEPH is quite common to see in the server environments and in the cloud environments. It's very good at, like I said, at storing object-oriented files or object files like VMs or databases. I don't know if I know too many databases that are running on Ceph or not, but it certainly has that capability. The Rados block service, or RBS, provides a distributed block service device to the Ceph client out here. So that's what actually makes Ceph look like a file system to the client. And that RBS service also includes a QEMU KVM driver, which allows the KVM systems to natively support Ceph without any change. The Ceph client provides a POSIX compliant system to the end user, and Ceph Rados can also be configured like, I forgot to mention this, but under Gluster you can also create geo-replication environments where you have two environments that are separate from each other, but the geo-replication allows them to exchange data so that the one basically is serving as a hot spare to the other. Or you're simply updating data in a geographical location to keep them both servers up and current. The Ceph architecture is more complicated. I believe they've added an admin component since I did this slide, but it has a metadata server. There's a monitor to manage the OSDs, which are that would be the storage device servers, and so you have, of course, the disks attached to those. And then you configure, you kind of configure this from the top down. You create your monitor, your MDAS, and then your OSDs, attach your devices to it, and then configure everything together, and then expose it to the Ceph client so that it can access that. Now, again, a Ceph client can also be on a server, and then that can in turn look like a NAS in order to share it out to non-Ceph clients. But yeah, Ceph is open source, and its assets were acquired by Red Hat in 2014. CERN, as of the last time that I looked, which was, of course, last summer, is migrating a proprietary system that they have over to Ceph, and I believe they're still working on it. They have massive amounts of data. At the time, I think it was around 300 petabytes of data. And the Ceph portion of it was at that time last summer was up to about 65 petabyte. Of course, when you have storage arrays that size, you're dealing with a lot of performance things that you're worried about and concerned about. So you don't just take 300 petabytes of data and slam it into an architecture that you're not sure how it's going to perform or what configuration you need to tweak in order to make it work at its best. But yeah, so yeah, and last time I checked, they had about 10,800 of these OSDs down here, which is that's a lot of storage. And of course, they were acquired by Red Hat in 2014, as I said, and of course, Red Hat was acquired by IBM in 2018. BeeGFS was introduced about a year later from Ceph. And so it's a little bit more modern and jump from the Lustre or Gluster or Ceph. It has a management service, which is out here, sits outside the bubble, and that is the registry and watchdog for all the other services that are running. It also has a graphical administration and a monitoring service, which runs as well in order to manage and set up the BeeGFS cluster. I have done a video on this, and we'll include a link in the video description of this one to that if you're interested in BeeGFS. It has a number of pieces. It has a metadata service, which is connected to the storage devices and the storage services. It also has a front end for the client called the client service, which allows BeeGFS clients to access the pool as a standard Linux file system. And of course, it does provide a POSIX level file system as well. BeeGFS runs on top of ext4, so it's sort of like Gluster in that respect. You can take just standard devices that are ext4, XFS, or ZFS, attach them together and onto the storage servers, and then connect them via the metadata service that's running on it. The difference between BeeGFS and all the others, however, is they do not need Fuse. They actually install a kernel driver, and so they have native support at higher rates of transfer than the Fuse-based systems do. BeeGFS also has native support for RHEL, both 5, 6, and 7, so that includes CentOS and Fedora. That also supports Sleuth and version 11 and 12, I believe, for those, and also Debian 7, 8, and 9, and of course that would also include Ubuntu. But from a kernel support perspective, they support kernels from 2.26 to 4.18. I don't know if they have plans to support any of the newer kernels, but right now they were kind of sticking with what Debian was doing at the time. Now, of course, Debian has moved on with Debian 10, and I don't know what their plans are to support Debian 10, but I'm sure that will be coming shortly. They do support different hardware architectures. The BeeGFS runs on x86, ARM, PowerPC, and Neon Phi. And it is open source, but you can purchase support for commercial environments if you want to from the company. So we've talked a little bit about, those are what I consider the present. And so I guess you just talk about the last topic, which is the future. So yeah, so when I did this originally, PCIe 4 wasn't out yet. It is now. And so I said that PCIe will replace 4 will replace PCIe 3. And of course, that is underway. SAS 4 will replace SAS 3 devices. Now, SAS 5 is currently in process, and in the case of PCIe, PCIe 5 has already been adopted, but there aren't any active solutions. There probably won't be for a while. But I can tell you that, of course, as you know, AMD Ryzen version 3 supports PCIe 4 on the X570 platform. And I know that they have plans to support it on the B550, I think. So yeah, PCIe 4 is definitely ubiquitous, and Intel in Tiger Lake, which is supposed to come out later this summer. And in fact, they've announced it and I believe it's probably going to be available at the end of this month. So yeah, that's supposed to have support for PCIe 4 as well. SAS 4, 22.5 gigabits per second, and I said it would replace SAS 3, although SAS 5 is already in the works, and I think the plans for that is about 45 gigabits per second. But don't hold me to that, because you never know what kinds of problems they're going to run into. NVMe over Fabric, or NVMe OF, and NVMe NAND both have new versions of that software as well. For NVMe NAND, it's 1.14, and for NVMe over Fabrics, I believe it was 1.1. Was the last version that was released in October of last year. I haven't seen any current work being done on SATA 3 at all. That, of course, is still 6 gigabits per second. I mean, it has its place. It's how we attach spinning Rust drives and some SATA-based SSDs, but I don't know what's going to happen with it. There is no activity currently on the board that I can see any improvements or anything happening to it. And so I say that spinning Rust drives will gradually disappear. That's probably not going to be true. At the time, the SSD devices were really coming on fast in their storage capacity, but of course they're really expensive right now. They still are, but there's some problems with the larger NANDs, and So I'm going to kind of change my mind a little bit based on what's been going on. So I don't think that spinning rust will disappear anytime soon, but I still think there'll be I still think those devices will be needed for long-term storage, even though they're a lot slower. That could change, however, with this, the DNA storage. Microsoft, like I said in the first video, had been working on this for about the past now 6 years. And and a couple of years ago, they demonstrated a DNA platform where they were able to read and write data to DNA strands. That could have a pretty large breakthrough because that could potentially store huge amounts of data for a relatively long period of time. DNA strands can last up to 200 years when properly stored, but I don't think Microsoft has designs to store it nearly quite that long. But the read and write times for it, of course, are very slow. Georgia Institute received a research grant back in January to work to advance DNA-based archival storage. So they could push this forward over the next few years. We don't know. One of the other promising technologies, particularly for spinning rust, and of course, the spinning rust drives have really been slowing down in their ability to store more and more data because the mechanisms that we currently have through CMR and SMR recording mechanisms are just not dense enough to allow more data to be stored on the drives without interference and errors without errors. But currently it's 6 terabytes for hard drives, and we're looking at 18 terabytes sometime this summer and 20 terabytes by possibly the end of the year. But one of the vendors, I won't say which one, said that probably we won't reach 50 terabytes until sometime well into 2026. So yeah, it's the ability for them to double every year. There was a Moore's law for the storage folks as well, but it is getting harder and harder for them. Skyrmion might be able to provide a solution. It's one of the research projects that's currently underway, and those are nano-sized structures that run on top of the magnetic film, and they rotate kind of like vortices on the surface of the magnet, and that creates the storage direction, the 1 or the 0, depending upon which direction the vortice is spinning. And that could be used to store much denser quantities of data than is currently possible. It also could allow data transfers to occur without using as much power. It has been successfully tested in liquid crystals, and in April of last month, the announcement of a new compound which makes it possible to store skyrmions at room temperature, and that wasn't previously possible. So it's just one more step down the road, right? So there's still work to be done to get this, if it ever is going to appear in a product. So I wouldn't expect to see this for a little while, 3 to 5 years, maybe longer. Depends on what they run into. Research projects are sketchy, right? If they run into a barrier and they can't solve it, they'll shelve it for a while. So I don't know, but there is active work that's being done in this arena, definitely. And quantum, the sci-fi version of storing data. So there's been quite a bit of work lately around this topic. As you probably can guess, the real problem is the qubit. It doesn't last very long. In most instances in nature, a qubit exists for only a few milliseconds, and then it's gone. The world record previously to the one that was set in September was, I think, 15 seconds. So it's probably, not going to be real stable for storing objects and storing data for any length of time. However, Delft University of Technology in the Netherlands in September 2019 set a record for both the number and also the duration, longevity of the qubit that was stored in diamond quantum memory. And it held about 10 qubits for about 75 seconds. So yeah, that's pretty good. That's pretty good. But it's still a long way from becoming practical. Hot qubits were also announced last year, and that was the ability to allow quantum computing to occur at Kelvin 1.5 degrees Kelvin, which is 15 times hotter than this particular platform that's shown here. This is one of IBM's Q series. So yeah, I mean, obviously, quantum has a way to go to become to become practical, and obviously, nature uses it quite effectively. So I suspect we would be able to as well. So anyway, that's where I wanted to kind of end up today, and yeah, I was talking a little bit about storage and kind of updating what I did last year as well. So I hope you enjoyed this talk, and if you did, please like and subscribe. And as always, I would love to hear from you guys as to what you're using. Are you using RAIDs? Are you using NAS? Are you using maybe one of the scale-out technologies like CEPH or Gluster or one of those? Let me know in the comments below. Hope to see you all again real soon, and bye for now.